The question pertains to the application of the 10-foot tap rule as described in the National Electrical Code, specifically Section 240.21 bone. There is a need to power two rooftop units, or RTUs, one requiring 150 amps and the other 40 amps, both operating at 208 volts, three-phase. The intention is to tap off an existing 2500 amp switchgear using a couple of fusible disconnect switches positioned within 10 feet of the switchgear. The point of confusion arises from Part 4 of NEC Section 240.21 bone, which stipulates that if the tap conductors exit the enclosure from which they are tapped, they must have an opacity of not less than 1/10 of the overcurrent protective device, OPT, protecting the main line. The specific question is whether this rule necessitates conductors sized for 250 amps, given that the tap conductors will run from the switchgear through a short conduit run to the disconnect switches. The answer is yes, based on the stipulation outlined in Part 4 of NEC Section 240.21 bone. If the tap conductors leave the enclosure from where they originate, they must possess an ampacity that is at least 1/10 of the line side overcurrent protective device's rating. Given that the line side OPT is rated at 2500 amps, the tap conductors are indeed required to be sized for a minimum of 250 amps. To further clarify the application of the 10-foot tap rule, let's delve into a more detailed explanation of NEC Section 240.21 bone and its various parts. Firstly, the general premise of the tap rule is to allow for conductors of reduced ampacity to be used to tap from a larger feeder or service, provided certain conditions are met. These conditions are in place to ensure the safety and protection of the electrical system. Secondly, the 10-foot tap rule is a specific exception that permits a shorter tap length compared to other tap rules, such as the 25-foot tap rule. However, because of the shorter length, the requirements are more stringent. Thirdly, focusing on the specific requirement in question, Part 4 of 240.21 bone addresses situations where the tap conductors leave the enclosure. This is a critical consideration as it affects the overall protection of the conductors. When tap conductors remain entirely within an enclosure, the enclosure itself provides a degree of physical protection. However, when the conductors exit the enclosure, they become more vulnerable to physical damage and other external factors. Fourthly, the requirement that the tap conductors have an ampacity of at least 1/10 of the OPT on the line side is intended to provide adequate short-circuit protection. In the event of a fault on the tap conductors, this minimum ampacity ensures that the overcurrent protective device on the line side will trip quickly enough to prevent damage to the tap conductors and other components. Fifthly, consider the practical implications of this rule. In the scenario presented, the 2500 amp switchgear is serving as the source of power. The tap conductors are being used to supply power to two RTU with load requirements of 150 amps and 40 amps respectively. While the combined load of the RTU is only 190 amps, the tap conductors must still be sized for at least 250 amps due to the 1/10 rule. Sixthly, the disconnect switches serve as a local means of disconnecting power to the RTU for maintenance or other purposes. These disconnect switches must be appropriately sized for the load they are serving and must also have the appropriate short-circuit current rating. Seventhly, the choice of overcurrent protection for the tap conductors at the disconnect switches is also an important consideration. This overcurrent protection must be sized to protect the conductors and the equipment they are serving, while also coordinating with the overcurrent protection on the line side. Eighthly, the NEC also requires that the tap conductors be protected from physical damage. This can be achieved through various means, such as installing the conductors in conduit or using other suitable protection methods. Ninthly, it's important to note that the 10-foot tap rule is just one of several tap rules in the NEC. Other tap rules, such as the 25-foot tap rule, may be applicable in different situations. The specific requirements of each tap rule must be carefully considered to ensure compliance with the NEC. Tenthly, to summarize, the 10-foot tap rule, as outlined in NEC Section 240.21 bone, provides a specific exception to the general requirements for conductor sizing. This exception allows for shorter tap lengths, but it also imposes more stringent requirements, such as the 1/10 rule. Furthermore, to better illustrate the application of this rule, let's explore a few additional scenarios and related considerations. 1. Consider a scenario where the tap conductors do not leave the enclosure. In this case, the 1/10 rule would not apply. The tap conductors would only need to be sized based on the load they are serving and the applicable overcurrent protection requirements. 2. Consider a scenario where the tap conductors are longer than 10 feet. In this case, the 10-foot tap rule would not be applicable. Another tap rule, such as the 25-foot tap rule, would need to be used. 3. It's important to ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and other applicable codes and standards. Improper electrical installations can pose serious safety hazards and can result in property damage or injury. 4. The NEC is a complex and comprehensive document, and it is subject to change. It is important to stay up to date with the latest edition of the NEC and any applicable local amendments. 5. When applying the tap rules, it is important to consider the voltage drop in the conductors. Voltage drop can affect the performance of equipment and can also result in overheating of conductors. The NEC provides guidelines for calculating voltage drop and for selecting conductor sizes that minimize voltage drop. 6. Grounding and bonding are also critical considerations in electrical installations. Proper grounding and bonding help to ensure the safety of personnel and equipment by providing a low impedance path for fault current to flow back to the source. 7. Arc flash is a serious hazard associated with electrical work. Arc flash can occur when there is a short circuit or other electrical fault, and it can result in severe burns, blindness, and even death. It is important to take appropriate precautions to protect against arc flash hazards, such as wearing appropriate personal protective equipment (PPE) and following safe work practices. 8. Coordination studies are often performed to ensure that the overcurrent protective devices in an electrical system are properly coordinated. Coordination studies help to minimize the extent of an outage in the event of a fault and to prevent nuisance tripping of overcurrent protective devices. 9. Power quality is another important consideration in electrical installations. Poor power quality can result in equipment malfunction, reduced equipment life, and increased energy consumption. It is important to take steps to improve power quality, such as installing power factor correction capacitors or using harmonic filters. 10. Energy efficiency is becoming increasingly important in electrical installations. There are many ways to improve energy efficiency, such as using energy-efficient lighting, motors, and other equipment, and by implementing energy management strategies. Furthermore, let's discuss some specific examples related to conductor selection and overcurrent protection to solidify the understanding of the 10-foot tap rule. If the calculated load for the 150 amp RTU includes a motor, the conductor ampacity should be at least 125% of the motor's full load current rating as per NEC 430.22. This ensures that the conductors can handle the motor's starting current without overheating. The overcurrent protection for the motor circuit should also be selected based on the motor's nameplate information and the requirements of NEC 430. For the 40 amp RTU, the conductor ampacity should be at least 125% of the continuous load, if any, plus 100% of the non-continuous load, as per NEC 215.2 or 220. This ensures that the conductors can handle the expected load without overheating. The overcurrent protection for the RTU should be sized to protect the conductors and the equipment, while also coordinating with the overcurrent protection on the line side. When selecting conductors, it is important to consider the ambient temperature and the directing factors that may apply. The NEC provides tables for determining the ampacity of conductors based on their size, insulation type, and ambient temperature. If the ambient temperature is higher than the temperature rating of the conductor ampacity must be derated accordingly. It is also important to consider the number of conductors in a raceway or cable. If there are more than 3 current-carrying conductors in a raceway or cable, the conductor ampacity must be derated as per NEC 310.15 current. This is because the heat generated by the conductors can cause them to overheat if they are not properly derated. In addition to the NEC, there may be other applicable codes and standards that must be followed. For example, local building codes may have additional requirements for electrical installations. It is important to be familiar with all applicable codes and standards before beginning any electrical work. Proper documentation is essential for electrical installations. This includes maintaining accurate records of conductor sizes, overcurrent protection ratings, and other relevant information. This documentation can be helpful for troubleshooting problems and for future maintenance and modifications. Regular inspections and maintenance are important for ensuring the safety and reliability of electrical systems. This includes inspecting conductors for damage, testing overcurrent protective devices, and tightening connections. By following these guidelines and best practices, you can help to ensure that electrical installations are safe, reliable, and code compliant. Always consult with a qualified electrical engineer or electrician if you have any questions or concerns. Furthermore, consider the impact of future expansion or changes to the electrical system. It may be prudent to install larger conductors or raceways than are currently required to accommodate future growth. This can save time and money in the long run by avoiding the need to replace undersized components. Surge protection is another important consideration for electrical systems. Surges can damage sensitive electronic equipment and can also pose a fire hazard. Surge protective devices, SPDs, should be installed at the service entrance and at other strategic locations throughout the electrical system. When selecting SPD, it is important to consider the surge current rating, the voltage protection level, and the type of equipment being protected. Harmonics are another potential issue in electrical systems. Harmonics are caused by nonlinear loads such as electronic ballasts and variable frequency drives, and they can distort the voltage waveform. Harmonics can cause equipment malfunction, overheating, and increased energy consumption. Harmonic filters can be used to mitigate the effects of harmonics. Power factor correction is another way to improve the efficiency of electrical systems. Power factor is a measure of how effectively electrical power is being used. A low power factor can result in increased energy consumption and reduced system capacity. Power factor correction capacitors can be used to improve the power factor. Emergency power systems are essential for critical facilities such as hospitals and data centers. Emergency power systems provide backup power in the event of a power outage. Emergency power systems typically consist of generators, uninterruptible power supplies, OPSs, and automatic transfer switches, ATSs. Lighting control systems can be used to reduce energy consumption and improve the aesthetics of buildings. Lighting control systems can include occupancy sensors, daylight harvesting controls, and dimming systems. Renewable energy sources, such as solar and wind power, are becoming increasingly popular. Renewable energy sources can reduce reliance on fossil fuels and can also lower energy costs. When installing renewable energy systems, it is important to follow all applicable codes and standards. Electrical safety training is essential for all personnel who work on or around electrical equipment. Electrical safety training should cover topics such as ART flash hazards, lockout-tagout procedures, and safe work practices. Remember, electrical work can be dangerous. Always take the necessary precautions to protect yourself and others from electrical hazards. By understanding and applying the principles of electrical engineering, you can help to ensure the safety, reliability, and efficiency of electrical systems. Always consult with a qualified electrical engineer or electrician if you have any questions or concerns. This information is for educational purposes only and should not be considered a substitute for professional advice. The NEC is a complex and constantly evolving document. It is important to stay up to date with the latest edition and to consult with a qualified expert when making decisions about electrical installations. In summary, the 10-foot tap rule, while seemingly simple, requires a thorough understanding of its nuances and its implications for conductor sizing, overcurrent protection, and overall electrical system safety. Adhering to the rule correctly ensures the safe and efficient operation of electrical equipment and protects against potential hazards.